Welcome, 8th period people.
You're not in frame.
Welcome, people who are in 8th period, 6th period, 9th period, the internet. If you're not here in this room right now, it means that I hate you. Good. Here we go. There was a homework assignment on the area problem. That's what we did on Tuesday. We solved the area problem. And there was a short homework assignment due today on this topic. Here it is. The function is f(x) equals x squared minus x cubed on the interval -1, 1. So we must make a graph of this. So the first thing that we can do is we can factor out an x squared, and we get x squared 1 minus x. That means that this is a function that I am very familiar with because it is just a cubic. What's up? Doesn't matter if I'm in the frame. My booming voice governs over all. Okay, it's x squared 1 minus x, and we can also factor out a negative. So that's negative x squared x minus 1.
Yeah.
Okay, so this is a cubic, and we know everything we need to know about this cubic. It has a double root at 0. It has a single root at 1. Because of the leading coefficient being negative, it's going to have end behavior like this. And without further ado, I make a graph of this function. When I plug in -1 into this function, I get 1 minus -1, so that's 2. Double root at 0 and single root at 1. Okay, so what kind of graph do I have? Something kind of like this. Something like that maybe is pretty much a decently accurate graph. If I wanted it to be more accurate, which I don't, I could like take derivatives and find a relative maximum, but like who cares? Okay. Also note that we are only interested in the area between the function and the x-axis on the interval -1, 1. So I will now erase these other things because they're like not important. And I have now this beautiful picture. All right, goal, find the area of this region. How are we going to do this? Well, we are going to split it up into a bunch of rectangles. How many rectangles? N. So we have n rectangles. And what is the width of each rectangle? 2 over n. That's because the entire width of the interval is 2, so the width of the interval is 2, dividing up to n pieces is 2 over n. Okay, and finally we have to decide which method we're going to use. Last class we talked about the LREM method versus the RREM method. What seems like the best thing to do at this time? I think the best thing you can do is RREM. I think that's just always a little bit better because it's just 5% easier because you don't have to deal with that whole like 0 blah 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 case. Okay, good. Now I shall happily draw pictures. Just what calculus is all about really. So there's a rectangle. Note that I'm following RREM, so I'm having split the function up into, having split the interval up into subintervals. I am using the value of the function at the right-hand endpoint of the subinterval as the height of my rectangle. So here's another rectangle, here's another one, and et cetera, et cetera. I'm just going to go dot, dot, dot. If you want to be cool, you could go and draw a picture of the ith rectangle, and maybe some more dot, dot, dots, and finally you get the last rectangle. The last rectangle in this case is like, you might argue, not even a rectangle, because as I am using the right-hand endpoint, it's going to be like a degenerate rectangle of 0 height. Good, I get the general gist. Now to the algebra. Well, if I have split this up into n rectangles, what is this little point right here? What are the coordinates of that point? I mean,
-1 plus delta x times 1.
Yeah.
Almost f of that.
Exactly, yeah. -1 plus, to get from here to here, I go over by delta x, which is 2 over n. So you could just write delta x, or you can write 2 over n. That's the x coordinate, and then the y coordinate is just f of that. Okay, someone help, what's that point?
-1 plus 2 at 2 over n, and then f that.
Yeah, and also that was the thing we did last class, which is to recognize that it's easier on your brain if you write it out in a kind of formulaic way that suggests the general formula. Okay, and then the third one, this is -1 plus. By this point I've scooted over 3 times, so that's 3 times 2 over n, comma, f of that. Okay, looking good. And then if I want to be cool, Connor, what is the ith rectangle?
It would be like
Wait. Careful, you just gave me the last rectangle.
Oh.
Let's give me the ith rectangle.
Uh,
This one's hard. Oh, if you can't see, you should move the spots.
this is not much better.
Okay, too slow. Someone take over Jenny.
Negative 1 plus I times 2 over n.
Yeah,
And then
comma f of that. Yeah, that's all. If it's the ith rectangle, then I've moved over I times. I think, Connor, what you are giving me is the nth rectangle, right? What is the nth rectangle? Let's do that one also.
Just 1 and then.
It is just one, but following the formula, what would the formula suggest it would be?
Negative 1 plus n and 2 over n, and then after that.
Yeah, and if you multiply n times 2 over n, of course you get 2, so that you do end up with 1, which is a suggestion that we're like doing this right. Okay, good. That is all the like thinking that's required. Now we can finally just get around to doing it. All right, what is this area? Well, the area of the first rectangle is going to be the width of the first rectangle times the height of the first rectangle, which is f of negative 1 plus 1 times 2 over n. And then the second rectangle is also going to have width 2 over n, but it's going to have height f of negative 1 plus 2 times 2 over n, etc., until we get up to the last rectangle, which is 2 over n is the width still. All of them have width 2 over n, and height f of negative 1 plus n times 2 over n. Alright, so if it helps you to write that out, so be it. If you're cool enough that you don't need to write it out, you can just go straight to the sigma notation. And if you go from I equals 1 to n, well, the point of spending all this time writing it out is that we see exactly what this pattern is. The only number which is changing every single time is the increment on the how much you're scooting over by 2 over n. And so the sum from I equals 1 to n of the width of each rectangle is 2 over n, and the height of each rectangle is f of negative 1 plus I times 2 over n. Cool? Alternatively, you could just read this directly off the picture by considering the ith rectangle. That's essentially what we're doing when we are writing the summation. We're saying this total sum is just, well, let's look at the ith rectangle. That's the width of the ith rectangle. That's the height of the ith rectangle. All right, cool? Say cool. All right, that's all the thinking. Now it's just a matter of cranking this bad boy out. So we do it. We pull a 2 over n out. And we take the sum from I equals 1 to n of, and then I just take this and I plug it into the function. So I get 2 over n I minus 1 squared minus 2 over n I minus 1 cubed. And now I have this giant evil, yeah, nice job, Beru. Giant evil thing that I have to like take care of, and so we do it. 2 over n times the sum from I equals 1 to n. I think the simplest thing to do is just crank it all out. So we get 4 over n squared I squared minus 4 over n I plus 1 minus. And now I have to cube that binomial, which I know how to do because like binomial theorem and stuff. So that's 8 over n cubed I cubed minus 3 times that squared. So that's 12 over n squared I squared plus 3 times that squared. So 6 over n I minus 1 zoom, 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 zoom. Now I think it is worth it to multiply everything out and combine like terms. This to me seems like definitely the easiest way to do this. So we take the sum from I equals 1 to n of, and is this all like on the video? Are you like, probably not?
Yeah, you went off a little bit.
I did go off a little bit. Just take it up from the algebra over here.
Okay, it's actually kind of, yeah, okay, I think we're good
Okay,
there.
good. And maybe we even need to, James, can close the window because there's a bad glare for some people. Yeah, that one, the other blinds. Yeah, good. And then now I'll like combine like terms. So this is negative 8 over n cubed I cubed. Yeah.
Oh, that's much better.
Good. Lines are pretty hard. I also learned at Wallops that teenagers don't know how to use brooms. I don't remember who it was, but I was watching some boy use a broom. And I was
Wait a
just
second, that was
was that you? It's
No,
like,
no,
oh my
this
god.
was good.
Alright,
Good.
good. It's like when you watch your parents use computers and you're like, and it's like you just want to like tear your own hair out because they're like not using all the shortcuts and stuff and you just want to like scream. That's what it's like watching you guys use a broom. Yo.
Not in Google.
The brooming is not okay, good. We're back. So negative 8 over n cubed I cubed, and now we have like boom, and then this becomes 12, so that's 16. So we get plus 16 over n squared I squared, and now we get a negative 4 over n minus a 6 over n. So that's minus 10 over n I, and finally there's a 1 minus n, which is another 2. Okay. Looking good. Now, I crank this out by dividing up into 4 separate sigmas so that I may apply the formulas. So that's negative 16 over n to the 4th times the sum from I equals 1 to n of I cubed, plus 32 over n cubed times the sum from I equals 1 to n of I squared, minus 20 over n times the sum from I equals 1 to n of I, plus 4 over n times the sum from I equals 1 to n of 1.
20 over n
20 over n squared. Okay, yeah. And if you need to make more stepped out when you do this yourself, so be it. Go at the algebra level that you're comfortable with so that you're not messing up. Alright, now I will apply the various formulas that I know for the summation sign. So this is negative 16 over n to the 4th. What is this? It's it's n squared n plus 1 squared over 4. That's the formula for the sum of the cubes. This is 32 over n cubed times. The sum of the squares is n plus 1,
Naveen,
2n
move your
plus...
head.
What's up? Oh yeah, Naveen, you're too tall.
Ian, you too.
Minus
There
20
you go.
over n squared times this, which is like n plus 1 over 2.
Perfect. Hold it there.
Plus 4 over n times, if I add up 1 n times, of course, that's just n. Alright,
Barely fits.
I did this whole wonderful, terrible thing, and now stuff cancels, so that's fun. So we get a and we get a and we get a 3 and 16, take an n out, this becomes a 10, die. Okay, good. What do we get? I guess I'll go like over here or something. So what we get is negative 4 n plus 1 squared over n squared, plus 16 thirds times, I'll multiply out this numerator, that's 2n squared plus 3n plus 1 over n squared, minus 10 n plus 1 over n plus 4. And this is basically the end. That is an expression which represents the area under the curve as approximated by n rectangles. On this function, on this interval, using Rem. If I were to plug any particular number in for n, like 8, then I would get the area as approximated by 8 rectangles. If I plug in 200, I would get the area as approximated by 200 rectangles, and if I plug in like 1 billion, I would get the area as approximated by 1 billion rectangles. I am crazy, so I'll plug in infinity. If I take the limit as n goes to infinity, then that will give me basically the exact area under this curve. And if I do this, it's easy to like just do this limit in your head. You get negative 4,
just
because
lean
that's like
back.
quadratic over quadratic.
Ian, lean back.
Plus 16 thirds times, this is like a leading coefficient 2 quadratic over like a regular quadratic, so that's just 2, minus 10 plus 4. And the 4's cancel, and so this is 32 thirds minus 30 thirds, that's 2 thirds. Whoa. Pretty exciting. Notice that not only have we solved this particular problem, but like Also, in the process, a subtle philosophical shift has occurred in that we have basically redefined area to be the result of this process. Just like when we were solving the tangent line problem, and we sort of had a general intuitive idea of what a tangent line was supposed to be, and then we solved the tangent line problem, which we sort of thought of as a geometry problem, via limits. We then sort of said, you know what, this whole limit of a quotient thing works out so well, let's actually define the slope of the tangent line to be the result of the process of taking the limit. Similarly here, we get so deep into what it means to find the area under a curve that we decide, man, this works out so well, then let this just be the definition of the area under a curve. Get it? That's what the calculus people did. Yo.
Isn't this kind of like where you have a circle and you split it up into a bunch of little segments to like make the...
It's exactly like that. Yeah, it's what we did on the very first day of the class, the method of exhaustion. It's the ancient Greek method of exhaustion, pioneered by Archimedes and others, which is to split an area or a volume up into an infinite number of small things and then add them all up. That's exactly what's going on here. Yep. But what kind of happened in the 19th century is people said, okay, this concept of area is kind of fuzzy for us. So I'm going to now define area to mean whatever you get when you do this process. Okay. The last thing to say is to just check, does this seem like a reasonable answer, 2/3? Math should like make sense. So I don't know, like if you draw a box around this, what's the area of that box? 4. So if the area of that box is 4, then that means like, that means one of these boxes is like, has like area like 1. So does it look like about 2/3? Yeah, kind of like close, especially since I just like freehand drew this cubic without any like real thought process. Yeah, if you take this little bit of area and this little bit of area and you stick it in there, that looks like that could be about 2/3 of that little bottom left-hand corner. Cool? Okay, good. Area problem solved. We are so great. I got a new problem for you. And people who were here yesterday do the same thing. Of course.
Oh,
We are going over here now.
Okay.
Alright. And if you have some wild idea, which you think is great, just keep it to yourself for a minute. Yeah, good. Okay, I got a problem. Find the area. Find the area under y equals root x on the interval 0, 1. Okay, go.
No.
So seemingly this is just exactly like what we've been doing. A function has been suggested. The function is y equals root x. From x equals 0 to x equals 1. And so we make a picture, we realize, alright, I need to find this area. No big thing. Can do this in my sleep. Let's split it up into some rectangles. How many rectangles would you like to use? N rectangles. So we use n rectangles. And therefore, what is delta x, the width of each rectangle?
1 over n.
1 over n. That is a fact. Isn't the whole thing is 1 over n? Alright, so let me just kind of like split it up. 2 over n, 3 over n, 4 over n. Start drawing some rectangles. Start figuring it out.
I just ask a quick question about RRAM and LRAM.
I'm using RM just because, why not?
Yeah, do you just like, it doesn't really matter that much if you're gonna just.
Yeah, more on that coming, but like, if you're gonna take the limit, then go to the beginning, the rest gets.
Okay.
What was saying, what happened?
You can't.
Are you stuck?
Yeah.
You're good, cry. If you're crying, it means you're doing it right.
Give up and cry.
Ah.
How do you square root?
It's a good life skill, also, to be able to cry on math, so.
Oh, wait.
No, I just can't put it right.
Less. Yeah, you're just like stuck.
Wait.
What? Yeah, I am stuck. Please, are you stuck? Are you crying? On the inside, good, that's what, yeah.
Isn't it just like?
I don't think anything good. Yeah. So look, we tried to do this, right? So far it seems like it's the same old, just like we did before 5 minutes ago. But when I take the sum from I equals 1 to n, and I add it up, what is the area of the ith rectangle? Well, the
Not yet, in a
height
minute.
of the ith rectangle is f of I over n, and the width of the ith rectangle is 1 over n. So far, so good. But then when I go to like proceed any further into this, I can take out the 1 over n, I guess. But then this is just like root I over n. And now I am beset with panic and doubts and confusion because I just don't know what to do with this. And I guess I could split up the square root and I could like factor out and like I get n root n. But still here I am faced with this. And I am stuck. I don't know how to sum up. I don't know how to take the sum of the square roots of the integers. And in fact, I'm pretty sure that formulas, even if it exists, it's got to be like weird and ugly, right? Because like, you know, you add up some like root 3s and root 5s, you're not going to get anything nice, agree? So that's like a gross formula. So I realize now that I was needing to be a little bit more humble about my solution to the area problem. Backing up a little bit, I have not really solved the area problem. Nobly, what have we done?
You're just.
Well, I mean, it seems as if like I was feeling really good like 10 minutes ago. Like we really solved the area problem. Like, I got like an exact answer, no estimate. Limit is equals to everything. Yeah, what about it all together all at once?
Solve the area problem.
Yeah, that's right. We solved, it turns out that really all we did was solve the polynomial area problem. We have not solved the area problem in general. This entire process that we did last class and just also 10 minutes ago will work to find the area of any polynomial. And I realized that this entire algorithm depends on my ability to have summation formulas for these things. And if I don't have the summation formula, then this doesn't work. Okay. Is there a way to do this? Yes, don't say anything. Hands down. Good. All of you get a virtual cookie for your wonderful ideas. No, a worse idea. But this will work. Solution. Subintervals of unequal widths. Of course. Subintervals of unequal widths. Alright. What the hell is that all about? Make this picture again, or I'm going to make it again. And now I realize, like, okay, here's where it all went wrong. Where it all went wrong is, is that I did not have a formula for the square root of I. And basically the square root is the problem, right? So I need to change things around in such a way, bless you, that I never have to plug, that I don't get any square roots. And the way to avoid getting any square roots is to make sure that you feed your square roots a healthy diet of perfect squares. If you feed your square root function a healthy diet of perfect squares, then you will not have any square roots left over. Okay, so what should the first, if you get the gist of this, what should the first, where should I make my first rectangle?
1, right?
That would be one big
Oh,
rectangle,
yeah,
that would be the whole thing.
You're right.
Instead of 1 over n,
1
over n squared. Were you here yesterday? No. You're actually in this class, right? Yeah, Reynolds says 1 over n squared. That is a great idea. Do you see why it's such a great idea? Because now I'm going to plug 1 over n squared into the square root function, and out comes 1 over n, the square roots just appear. Okay, cool. What is the next spot I should try to make a rectangle? That's an idea. 1 over n to the 4th is actually like back the other way. 2 over n squared, almost. Or do you mean 4 over n squared? Yeah. 4 over n squared. Excellent choice. Because now when I plug that into the square root function, I get 2 over n. Bless you. Next one?
9 over
Okay. So this is kind of weird. We're having these rectangles which are getting wider and wider. Okay, and now we'll skip to the nth rectangle, which is going to be the biggest one of all. That will be following the pattern. That would be like n squared over n squared. Yeah? Say yeah. Okay. All right. All right. This is weird enough that we need to talk about this. All right. I hereby define let little c sub I be the right endpoint. The right endpoint of the ith subinterval. And having defined c sub I as the right endpoint of the ith subinterval, let's make sure we all got this under control. Like, what's c1? What's the right endpoint of the first subinterval? 1 over n squared. What's the right endpoint of the second subinterval? 4 over n squared. C sub 3 is like 9 over n squared. So what is c sub I? I squared over n squared. That's nice. Okay, so that's basically my formula. What I'm basically saying is, we're going to be using rectangles of unequal widths, and here's how we're going to do it. We're going to go through that interval from 0 to 1, and everywhere at the point I squared over n squared, put a little dot, and that becomes the right endpoint of that subinterval, and then plug those numbers into the function and make your rectangle. Kind of cool? Okay. Good. Well, this is very weird because my rectangles are now of all unequal widths. So what are these widths actually? I hereby introduce delta x sub 1 to refer to the width of the first subinterval. What is delta x sub 1? 1 over n squared is the width of that first subinterval. What is delta x2?
3 over n squared.
Careful. 3 over n squared, yeah, is the width of that second rectangle. Delta x sub 3. Oh, tease a pattern. Yeah, DJ, what is delta x sub I maybe? Just kind of like use some guessing checks so you get it right.
Okay, hold on. It's this way. Is it I plus I minus 1?
Yep. Yeah, wait, I think so. Wait, you're panicking under the spotlight.
An
Yeah,
idea, is it 2I minus 1 over n squared?
Yeah.
I think that's right. Is that what you said? I plus I minus 1? Is that what you said? Yeah, exactly.
Oh, okay.
Yeah, it's basically just it's like the ith odd number. And that's like a well-known fact about the patterns of the gaps between quadratics are the odds. And so yeah, that's what we're going to Alright, so this is what VJ and James think it is. Can we do maybe a little bit better than just guessing what we think the formula is by pattern recognition? Can we maybe like prove what the formula is? I think we can. What is the width of the ith subinterval like in general, like in words or math? Exactly. Shiv's like, yo, the width of the ith subinterval is the right endpoint of the ith subinterval minus the left endpoint of the ith subinterval, which is just the right endpoint of the previous subinterval. You guys with me? Lots of like, notation going on here. Okay. Well, we have a formula for c sub I. It's I squared over n squared. And what is c sub I minus 1? I minus 1 squared over n squared. And if we just like do all that, like what do we get? I think it just like works, right? Yeah. Yeah, we get I squared minus 2i plus 1 all over n squared. And that just is, running out of space, certainly probably illegible for people at home.
Ben, just like completely like remove, it's like put your head like under your desk or something.
Nah, it's like fun.
Along
we
you
get
too.
we get 2i minus 1 over n squared. So now we've actually proved, I'll erase this question mark. This means that VJ and James like did actually have it right because like it all works out. Okay. Alright. Now we have to have like a weird conversation about these rectangles because like now, alright, things are sort of weird because alright, as I move to the right, the rectangles get wider and wider, right? Okay, but also at the end, what am I going to do? The very end of this problem, if we ever finish. Yeah.
Make like infinite of them.
Yeah, we're going to make infinite of them. In other words, we're going to let n go to infinity. So as n goes to infinity, can you imagine what is happening to these rectangles as n goes to infinity?
They're getting
Really
really
They
small.
get really thin. Are all of them getting thin? Now I have to worry a little bit because like they're all getting different thin or something. Are you as worried as I am?
No.
Wait,
They're all.
I mean, I think like,
You think it works out?
well, I was gonna say like it's kind of weird because I think the last one's just looking like 1, right? And then
Yeah, we should check this
The whole
out.
thing.
He's worried about the last rectangle, which is the good rectangle to be worried about because it is the widest of all of them. Okay, how wide is that last rectangle, the widest of all? What is the width of that last subinterval? Yeah, we have developed and in fact even proved a formula for the width of the ith subinterval. So I can just plug in n and I get that the width of the last subinterval is 2n minus 1 over n squared. Okay, now I'm